All right, this is a lesson about the applications of logs and exponents. We've done exponential growth and decay, the kind of basic stuff you did in Algebra 1 and Algebra 2. But we're going to go a little bit further in Precalc. We're going to talk about Newton's law of cooling, and we're going to talk about half-life and all those kind of good things. So the first one here is, oh wait, I wanted to, please take out your calculator and your piece of paper and write these down. When I type stuff in the calculator, make sure you're typing it and getting the same answer. If you're not, stop, go back, see what you're doing different. Okay? I will turn my calculator on for at least one of these. Otherwise, I'm going to do it off on the side because it takes me so long to type. All right, so Newton's law of cooling says an object that has been heated will cool to the temperature of the medium in which it is placed, for example, the surrounding air or water. The temperature of the object can be modeled by this equation, or this one, which is the one we're going to use. And sometimes I use M for medium, and sometimes I use S for surroundings here. Sorry, it's the same thing. Okay, surroundings or medium. Means the same thing. I will tell you that both of these formulas assume that their surrounding medium temperature essentially remains constant. Okay, so these are actually kind of an oversimplification of what happens because, for example, when you take a pizza out of the oven, you set it on the counter, it doesn't really heat up your room very much. The pizza itself doesn't cause the room temperature to change. Your oven might, but the difference would be if I took a mug full of cold ice water and I threw a hard-boiled egg just out of boiling water into that cup of cold water. It's a small enough medium or surroundings that it would actually change the temperature of the water. So this kind of ignores that. I just want to talk about the science a little bit here. But we're going to use this formula right here. The issue is going to be that we have to do this twice because they're going to give us enough information to help us calculate first the K value and then go back and find the time to finish cooling something. So it says down at the bottom of this slide, okay, the cooling constant K will have to be found for each substance first and then find the time to reach a desired temperature. All right, so I'm actually going to go to the next one here. It says, Newton's law of cooling, a cup of coffee has cooled from 92 degrees, which was the original temperature, to 50 degrees, its final temperature, after 12 minutes. Little t here is time up in the exponent. In a room at 22 degrees, so the room itself is the surrounding temperature or the temperature of the medium. So T sub S is this number. How long will it take to cool to 30 degrees? We don't need this yet. This is for the second half of the question. We don't use this at all. This is for the second half. We're going to go back and use this as the final temperature after we find K. Okay, so first things first, we write this down. The final temperature minus the surrounding temperature equals the original temperature minus the surrounding temperature. Excuse me? Sorry there. COVID Joe was checking on me from the basement, but he doesn't really have COVID, I don't think. I think his test is going to be negative, and then I'm going to get to come back to work. All right, anyway, final temperature was 50, surrounding room was 22, original temperature was 92, or almost boiling in Celsius, minus the surroundings of 22. And then we have e to the negative, and we're trying to find K when the time was 12 minutes. All right, so we have to do some arithmetic first. 50 minus 22 is 28. 92 minus 22 is 70. And I'm just going to rewrite this as negative 12k. Just switching the order on their multiplication there. The next thing we have to do is isolate. So we're going to divide both sides by 70. And I'm going to go ahead and change that to a decimal. Let's see, 28 divided by 70 is 0.4. I thought so, but I thought I should not make a mistake. All right, now we're really left with a pretty easy question. We just need to take the natural log of both sides. This is going to come out in front as a negative 12k. And then the natural log of e is just 1. So we end up with the natural log of 0.4 equals negative 12k. We can divide both sides by negative 12, and we find k. So the natural log of 0.4 divided by negative 12 is 0.0764 if I round. So that's k. All right, natural log of 0.4, make sure you close that parenthesis, and then divide it by negative 12. So the k value is 0.0764. It should be positive when you do these, because there was a negative that came with the formula, and that's what makes it a cooling. It's negative kT, but this is the cooling constant, so it should be positive. If it's not, you messed up somewhere. All right, now we get to go back to the top here and start all over, because we want to know how long it's going to take to keep cooling down to 30 degrees. So we're going to put in here a final temperature of 30 now. And K is 0.0764. And we're trying to figure out how long that will take. So we're going to start over. I'm going to try to write small here. T sub F will be 30. I'm using this red formula all over again, okay? 30 minus T sub S, the room is still 22, equals, we started at 92 and we're going to keep that as our original temperature because we're going to say that how long did it take from the beginning, not how much longer. And then e to the negative, and let's see if I can. Try to squeeze this in here, 0.0764 T. Okay, I can't squeeze that in there. I'm crazy. Try to move all of this. Oh yeah, that's working so well for me here. All right, that's a little better. Sorry, I knew I was going to run out of room here. Anyway, 30 minus 22 is 8. 92 minus 22 is 70. E to the negative 0.0764 T. That's a little better. You can read it now. First thing we still have to do is isolate, so we're going to divide both sides by 70. So I have 8 over 70 equals e to the negative 0.0764 T. Then I'm going to take the natural log of both sides. And I'm going to bring this out in front. So I'll have negative 0.0764 T times ln of e, which is just 1. And 1 times anything is itself. Now, remember, this was the log of the whole quantity, so you have to do the natural log of 8 over 70, And then we're going to divide both sides by negative 0.0764. Natural log. 8 divided by 70. Okay, I got negative 0.216, and then I'm going to divide that by negative 0.0764. And I get 28.4. So we're going to say 28.4 minutes is how long it would take from the time we took it out of the microwave at 92 degrees to the time it was down to 30 degrees. Okay? So it's a matter of plugging things in and finding, just do your equation solving and finding the k value and then plugging everything back in and finding the little t up in the exponent. But both times you're finding something in the variable in the exponent, so you have to do the log of both sides after you isolate it. All right, I'm going to go through one more. This time the oven, cake is removed from the oven at 350 degrees. That was its original temperature because it sat in the oven long enough to get that surrounding temperature up of the cake all the way up to here. It cools to 120. This was its final temperature after 20 minutes in a room at 65 degrees Fahrenheit. So that's the temperature of the surroundings or the medium. How long until it gets down to 90 so we can finally frost it? Or ice it if you're Canadian. But we don't need that temperature yet. That's later. We have to find K first. So I'm going to use this formula right up here. Okay. TF is 120 minus TS, which is 65, equals T sub 0, which is 350, minus the surroundings again, which is 65. And then it's e to the negative k times t, which was 20 minutes. All right, so don't make a silly mistake like I always do. 120 minus 65 is 55. 350 minus 65 is 285. We have e to the negative 20k. I'm just going to switch the order so it looks a little nicer. First thing we do is divide the 285 over here. Then we take the log of both sides. And we use ln because we had an e in the problem. Then we can move that out front. So we have negative 20k times natural log of e, which is just multiplying by 1. And over here, we can type that in right away. I usually just write it down. And then we're going to divide both sides by negative 20 here. And we should get a positive decimal k value. So the natural log, 55 divided by 285, and then close the parentheses, and then divide by negative 20, and I have 0.082, and it would round to 3. Okay? That's a reasonable k value. Now we're supposed to do this over again and figure out how long until we get down to a final temperature of 90 degrees. So again, we can put frosting on. Okay? At least that's my idea. This is a good time here is let's make it worthwhile. Let's talk about putting the frosting on. Nice fudgy chocolate frosting. All right. So TF is our 90. We're going to fill that in here, and everything else stays the same except the K value goes in now. So we will have 90 minus 65 equals 350 minus 65. E to the negative 0.0823 times the time we're looking for. 90 minus 65 is 25. And this is still 285 over here. E to the negative 0.0823t. We're going to divide. Then we're going to take the log of both sides. And this will come out in front. So we have negative 0.0823t equals whatever this is. Maybe I'll type it in this time. The natural log of 25 divided by 285 is 0.2. Nope, just kidding. Negative 2.4336, and then I'm going to divide both sides by negative 0.0823, and I get 29.57, or about 30 minutes, 29.6 minutes until we can put the frosting on. Okay? I know those are long and complicated. I will be very honest and tell you, there is one on the quiz, but on the quiz I tell you the K value and you just have to find the time, I believe is the way it goes. I know you have one to solve kind of like this, but it's only one step instead of two. All right, I'm going to go through a few other examples here. This is the half-life formula. It says when you take an initial amount of a substance, you multiply it by 1/2, but instead of doing it to some power of, say, 8 or 10 or 20, if its half-life is every 6 hours, then you divide by 6 here. So in 24 hours, it would have 6 times. Did I say 4 hours? Yeah. So 24 divided by 4, you'd end up with a power of 6. So it's the amount of time that has passed, but H is the length of the half-life of each half-life or doubling time or whatever you're talking about. Okay, so the half-life of radium-226. The 226 is part of its name. It's not a number we need in this problem. This is the half-life, so this is the H. Suppose we have an initial sample, so this is P of 120 milligrams. How much will remain after 4,000 years? That's an X or a time. So this one, we would just write 120, and then it's 1/2 or 0.5 to the half-life is, the time is 4,000. Divided by the half-life, which is 1600. So I should do that one here so you're sure you got it. You can't take 120 times 1/2 and make it 60. Guys, the exponent comes first. So you can type it that way because the calculator knows the exponent comes first. To the, and then it's 4,000 divided by 1600. If you had an older calculator, you would need to put parentheses around that exponent. I think I can even show you that. I haven't done this before for a while for you guys. But I think, no, it's at the top. Just kidding. I think if I put this in classic mode, and I were doing that problem 120 times 0.5 to the power of, and then you would have to put in parentheses because it's not going up in that little box. Okay, if you have an older calculator, it was going to look like that. Okay, I'm going to go back and put mine in my pretty math print mode. All right, but either way, we got that it's down to 21.2 milligram sample. Now, this says how long until there will only be 10 remaining. So we want 10 at the end. If we started with 120 and it's being halved, but we don't know how long, but we know it's only being halved every 1600 years. So this is only a one solving, but we have a lot to do, and we can't do 120 times 0.5. Again, guys, you have to divide both sides by 120, which I'm just going to leave 10 over 120. And over here I have 0.5 to the x over 1600. Now, because the x is in the exponent, we're going to need to take the log of both sides. Doesn't matter what kind. I usually do ln because it's shorter to write, but I'll do log. But remember that x over 1600 can come down out in front here. Now, the difference on this problem, once we bring it down there, you can't cross this out. The log of 0.5 does not go away. So you can do this however you want. You could do a bunch of typing now and then just solve for x. I usually don't pick up my calculator until I have to. If I divide both sides by the log of 0.5, okay, then I will have x over 1600 equals, and whatever I get over here, I guess now would be a good time to type it in. The log of was 10 divided by 120, all in one, and then that's divided by the separate log of 0.5, right? And it will work if you do ln in both places, you get the same answer. So I have 3.58496 something, and then I'm to have to get rid of this divided by 1600. I'm going to multiply by 1600 because what's happening is it takes 3.58 half-lives, okay, to get it down to that quantity of 10 milligrams. So we have to multiply by the 1600 that is the length of a half-life, and we end up with about 5736, I'm going to round. For how long it's going to be before it gets down to that amount. Did I do this? Where did I write that number down? Anywhere? 3.585, kind of. Whoa, I don't know what just happened. And then we multiply by 1600. Okay. This is a doubling problem, but it's very, very similar. And it doubles every 8 hours. So it says how long until a single fruit fly. So our initial amount, I don't remember what they used. P sub 0 is what I want to use, but was one fly. The doubling time is like our half-life. Okay, so it's every 8 hours. But instead of halving, it's doubling in here. So we have T over 8. It does it every 8 hours. It doubles, starting with one fruit fly, and we want it to become 1,000. Well, as soon as we divide by 1, we get 1,000. If we take the log of both sides, now some of you could do that in your head, because we can move this guy out front. The log of 1,000 is actually 3 when you're doing base 10, but I'll just leave it. I'm going to divide both sides by the log of 2. So then we have T over 8 left over here equals, if I type the log of 1,000, which is 3, divided by the log of 2, I get 9.9 9, 6, 5, 8. Then to get rid of that divided by 2, or divided by 8, I'm going to multiply that answer by 8, and I get 79.7 hours, was it? How many hours? Yes. So almost 80 hours to get up to 1,000 fruit flies if they're doubling every 8 hours. All right. This is a half-life question again, but it uses a percent. It says a wooden artifact from an ancient tomb contains 65% of the carbon-14 that is present in living trees. How long ago was the artifact made? So it originally had 100%, contains 65%. This is what's left. It's down to 65% of what was originally 100%. It is a half-life question, and the length of the half-life is 5730. All right, we can get rid of the decimals, or the percents, I'm sorry, by switching over to decimals. Then as soon as we divide by 1, we have 0.65 still. 1/2 or 0.5. T divided by 5730. Then we're going to take the log of both sides, and it doesn't matter what kind you do. And this guy comes out in front. Then I'm going to divide both sides by the log of 0.5. Because I'm trying to isolate T. Whoops, that's just 0.5. So now I have T over 5730 equals the natural log of 0.65, close parenthesis, divided by the natural log of 0.5 is 0.62149. If I multiply that by 5730, I get 3561 approximately years old. Okay. I hope I can manage to edit out where I messed up there the first time through. All right, we have one more problem. Gosh, this video is longer than I wanted it to be. Sorry. This is a really important concept, though. Logistic growth happens all the time to populations in our environment. It models things that increase and grow quickly and then reach what's called a carrying capacity. For example, I live out at Candlewick Lake. If we were to throw boatloads of fish into the lake, there would eventually, they would reproduce quickly, but eventually they would reach a maximum that the lake can only hold and sustain so many fish. Okay? Same thing, the environment at Rock Cut can only sustain and hold so many deer before they start dying from starvation or something because there's not enough in the environment that they are contained in. All right, enough food, whatever. This is the form that will take. The top number up here, A, is going to give you what in this one down here is called C. Sorry, I just grabbed this picture off the internet. But the carrying capacity is generally that top number, unless this is not a 1 down here, and then they can do something funky. But in this form, what you have to remember when you type this in your calculator, you're going to put things in Y1, and you're going to have the carrying capacity divided by, and then you have 1 plus some number, and then E to the, and then some numbers here, and the T is going to be an X on your calculator, okay? Or if you had an older calculator, you'd need extra parentheses up there. But make sure you have those parentheses in the denominator. So, it says the population of frogs after T years in a pond is modeled by this equation. So I typed it in, 120 divided by parenthesis, 1 plus 14E to the power of negative 0.6, and I put in an x instead of a t. The projected maximum number of frogs is the carrying capacity for this pond, which is going to be 120, and you will see that when we graph this. Now, this graph is going to have the shape we just looked at. It's going to go like this. But to see that, we need to set a window where this is time. So we might have to look out a long ways. I think I put in 30 years to see how many frogs. Okay. I know though that it's going to cap out at 120. So this is the number of frogs. So I put over here for the y values like 0 to 150 for my window. So if I slide this down, the window I used was 0 to 30 on x's and 0 to 150 up and down. So then when I hit graph, this is what I got for a picture on my calculator screen, okay? Then the first question said, what was the initial population of frogs? So you can either put in t equals 0, or on the graph, just do a trace 0. So I did that. I went trace 0, and down here it says 8. Everybody see that? 8 frogs. Please do this question on your calculator and make sure it's working. Otherwise, you're going to do this one on the quiz, and there is one on the quiz of these, and you're not going to know how to type it in correctly or on homework or something. Now, this is the trick. When will there be 100 frogs? And this is the question it asks on the quiz. The way to solve this is to put into y2 the line 100 and then find the intersection. So, all right, move this down. I went to y2 and I put in the line of 100, and it lovely graphed it in a different color. So I'm trying to figure out here, when did the number of frogs hit that line? Okay. Oh, great. I don't have it on here. So I have no idea if it's still typed in here. Oh, it is. Thank goodness. So I'm going to go down here and put in 100. And then I'm going to find the intersection point, second trace, choice 5. And it says 7.08. So about 7.1 years until we have 100 frogs. And again, the carrying capacity should be that that top number of 120. If I pull the calculator back up here real quick and I trace on this blue one, you will see it is going out and getting very, very close, and eventually it will round to 120 frogs. Okay, there's no point in doing this because I'm telling you that that's what the top number is. All right. So 35-minute video. I'm sorry it was so long, but please, please, please do the examples on this sheet, because otherwise you are desperately going to struggle on the quiz